Hi guys, just going to do this quick unedited video going over some of the solutions to homework 8. Please check the comments that were returned to you on Sakai, go over your answers, make sure that you have resolved any questions there. One thing I want to dispel is I've seen this number crop up a ton on your homework and it's almost always wrong. Is this number 22.4 liters? Some of you are using this all the time as like a way to get moles, and it's totally incorrect. Okay, here's what's going on. In the ideal gas law, if you want to solve for the number of liters in 1 mole, you would take 1 mole times the ideal gas constant times some temperature, and you divide it by atmospheric pressure. Okay, so if you plug in a temperature of 273 Kelvin, then you get a volume of 22.4 liters, right? So that's where this number comes from. It's the volume of 1 mole of ideal gas at atmospheric pressure and 273 degrees Kelvin. The problem is that a lot of you are using this when the temperature is not 273. If the temperature is 298 degrees Kelvin, then the volume of the ideal gas at 298 degrees Kelvin at atmospheric pressure is 24.4 liters. Overall, I think this is just a bad thing to memorize, and you should just use the ideal gas law, because that's all it comes from in the first place. Second comment here is going through question 1. We're talking about a Carnot cycle here in question 1. So very simple to draw on the TS diagram. We have a hot temperature of, say, what was it, 358 Kelvin, and a cold temperature of atmospheric, so 298, right? So that's your box. When I was asking for the delta S, maybe this was a little unclear, but the delta S for the Carnot cycle is just this width. Right, so how wide is it? So that's kind of interesting. You could take the QH value divided by TH, that would give you delta S. You could take the QC value divided by TC, that would give you the same value for delta S. Or you could actually use the area of the rectangle and take the work divided by the temperature difference. You wouldn't even have to calculate the efficiency for that. You could just use the temperatures that are given and the work of 600 joules. That would also give you the delta S. So it's 10 joules per Kelvin of entropy width for that cycle. The other question on the other part of question 1 that was tough was this volume and pressure stuff. Here you really gotta look at the cycle. If you just try to plug into some random formula, you're going to be totally in a daze. So this cycle has 1, 2, 3, 4 for its corners. And on the PV plot, we're talking about isothermal, or adiabatic, isothermal, adiabatic, isothermal. Same direction of arrows, same corner order. So 1, 2, 3, 4. So it's clear here that the max volume is at point 4, and point 4 is connected to location 1 by an isothermal step. So 4 to 1 is isothermal, and so along an isothermal step, the heat is moles times ideal gas constant times the temperature of the isotherm times the logarithm of the volume ratio. So as we go from 4 to 1, we're actually going from high volume to low. So our final volume is 1, and our initial volume is 4. And that's for the heat absorbed by the substance from 1 to 4. It's actually going, 1 to 4 is going to the left on the plots. So that's a an ejection of heat from the substance to the cold reservoir, right? So when you get your heat for QC, you change that into a positive number, so then when you go to relate this to volume 1 and volume 4, you will put that minus sign in front of it there. So this is the way, volume 1 is the 5 liters from the problem statement. This is the right way to solve for volume 4. For part E, where you get the pressure, then you're looking for the pressure of location 2. The pressure at location 1 is atmospheric. And so pressure 2 and pressure 1 are related by this adiabatic step. 1 to 2 is adiabatic. And so along an adiabatic curve, we have pressure times temperature to the power -1 minus F over 2 being constant. I know we haven't seen that as much in the notes, but it is an adiabatic relation. You can go back and find that from the material on test 2. This is the way to plug in the two temperatures and the pressure at location 1 to get the pressure at location 2. Okay, that covers question 1. So then going on to question 2 about the Stirling cycle. I know we've got a chance now to do a lot of Googling about Stirling cycles, and I want to emphasize here that the ideal Stirling cycle is not the same as an optimized Stirling engine, okay? So you may read places that the Stirling engine has the same efficiency as the Carnot cycle or something like that, and that's an optimization that includes a special device called a regenerator. It means that the optimized Stirling engine is actually using 3 reservoirs, and some of the heat is going into one reservoir and then coming straight back out to save on the heat that's actually coming from the fuel source. But for an ideal Stirling cycle, we consider all of the heat to come from the hot reservoir and all of the heat to be ejected to the cold reservoir. No other reservoirs accessible. So for the Stirling cycle, we actually have a heat value for all 4 steps. None of them are 0. So when we look at the cycle, this is really important. This is something that I really expect you to nail, okay? When you look at the cycle and you have each step labeled, you should be able to look at this cycle and say, okay, this is volume, we labeled this as VS, we labeled this as VL, the bottom isotherm here is TC, the top isotherm is TH. You need to be able to look at this cycle, and if I ask you, what is the heat absorbed by the working substance from 2 to 3? You need to be able to find out that expression, right? It's going to be in one of your tables. You go to the table, you look for heat. It's an isothermal step at TH. So if we have isothermal at TH, then the Q value, which always represents a Q absorbed, is going to be nRTH times the log of the final volume over the initial volume, right? So that's just a given that we've talked about isothermal expansions quite a few times in the past. That's for 2 to 3. You also need to be able to look at, say, 3 to 4. What's 3 to 4? Well, 3 to 4 is isochoric at a volume of VL. And what's the heat for that step? Well, an isochoric step has a heat of F over 2 NR times the temperature at the end minus the temperature at the beginning. Okay, now comparing this to the diagram, T4 is equal to the cold temperature reservoir TC, and T3 is equal to the hot temperature reservoir TH. So this difference in parentheses here is going to be clearly negative because, TH is a hotter temperature than TC. So this Q value here for 3 to 4 will come out negative, and that signifies that that's a heat ejection instead of a heat absorption. So before you wallow around in efficiency values and work, if you're doing these cycles, it's really good practice to just look at every step, figure out its Q value in terms of how much heat is absorbed. If it comes out negative, that means it's ejected. You get those Q formulas for each step. Then, secondly, you can start assigning them to, well, which reservoir did it go to? Was it cooling off? Was it gaining entropy or losing entropy? Which reservoir does that heat assign to? Do I need to change its sign or anything? Okay. So the answer for question 2, I apologize for having two part C's here, but the answer for question 2 for the efficiency was 1 divided by 1 over the Carnot efficiency plus F degrees of freedom over 2 times the natural log of the large volume divided by the small volume. Okay, and if you simplify your answer, then it can get down to this. And when I say to write it in terms of gamma, writing it in terms of F is okay because F and gamma are just in a sort of one-to-one relationship. So this is clearly going to be less than 1 over eta c because you're adding something in the denominator, and so that's going to be less than the efficiency of the Carnot engine. Okay, so that's question 2. Then for question 3, we're taking this Stirling cycle and we're turning it around. So I'm just going to reuse the same drawing here. And renumber the corners. So corner 1, corner 2, corner 3, and corner 4. So the arrows are going now counterclockwise around the cycle. I'm going to relabel the numbers to go in a consistent direction with the arrows. And then once again, as I suggested, first find out the heat expressions for each one. Right, so like, what's Q1 to 2? Well, it's isothermal, it's at a temperature of Tc, so it's going to be nRTc log of VL over Vs. Right, that's a positive value for the Q, so it's a heat absorption. That's what we expect for this low temperature expansion in the refrigerator. It's absorbing heat from the cold reservoir there. So when we look at this Stirling cycle as a refrigerator, we have to first find out the heat values, and then we have to think about what reservoir it has to come from. This is really kind of helped out by looking at the deciding what reservoir it's absorbing or ejecting heat to really is helped by looking at the TS diagram. So that's why I had you draw this for the cycle. We've got an isotherm at Tc, an isotherm at Th, and the segments of constant volume are exponential in shape. Okay, so there's our isotherm, and these are our lines of constant volume on this plane. So 1 here, 2 there, 3 there, and 4 there. And so for the heat absorbing or ejecting, right, from 1 to 2, we're absorbing heat from somewhere. From 2 to 3, we're also absorbing heat from somewhere. So 1 to 2 must be an absorption. 2 to 3 must be an absorption. We know that purely because it's moving to the right on the TS plot. 3 to 4 must be ejection, and 4 to 1 must be an ejection purely because they're moving to the left. Now, what reservoirs could these come from? Well, we want 1 to 2, to be an absorption of heat from the cold reservoir in a refrigerator. So that's going to make sense to be a contribution that's positive to QC. 2 to 3 is also an absorption. We'd love it if that could absorb from the cold reservoir, but look at what happens here. it really can't absorb from the cold reservoir along 2 to 3 because it's already hotter than the cold reservoir. So 2 to 3 has to be an absorption. The only reservoir that can accomplish that for us is the hot reservoir. So this is an absorption into heat from the hot reservoir. So it's not what we want to happen in a refrigerator, but we can still make it work as a refrigerator, sort of if the heat on 1 to 2 is long enough. All right, 3 to 4 is ejection. That's pretty easy to associate with the hot reservoir, QH. And then 4 to 1 is also an ejection. Look at 4 to 1 though, its temperature is below the temperature of the hot reservoir, so it can't eject heat to that hot reservoir anymore. Along 4 to 1, it's got to eject heat to the cold reservoir. So 4 to 1 is ejecting heat to the cold reservoir. Right. So when we calculate the net heat ejected, the net heat absorbed from the cold reservoir, we've got a positive contribution from heat of 1 to 2. That's going to give us a an isothermal one, right? nRTC log of VL over VS. So that's the heat from 1 to 2. But then we got this negative contribution from 4 to 1. It's not what we want, but we hope that the refrigerator works anyway. So we have to subtract F over 2 NR times the temperature difference, TH minus TC. That's the heat value for this isochoric step from 4 to 1. Right? So this comes as a positive contribution from 1 to 2. This comes as a negative contribution from 4 to 1, because this one's coming from the absorption step here, and this term is coming from the ejection step here. So there's a possibility that if these volumes are not big enough or different enough, that this QC could end up not even being positive, and then it wouldn't work as a refrigerator. So that's what we're asking in part C. With that expression for QC, what's the relationship on the volumes that makes QC positive? So you would just use this expression for QC. You'd be plugging in to an inequality and then rearranging the inequality to solve for the large volume, basically, in terms of the small volume. So you would get VL must be greater than VS times exponential of F over 2, basically this stuff, F over 2 times TH minus TC over TC. Okay, so it turns out that it's not hard to build a Stirling engine that just has a large volume, large enough to make it bigger than this right-hand side, and then it still works as a refrigerator. But there's the possibility that if you're just eking back and forth your piston between two really close volumes, that you're not going to refrigerate at all. You're just going to kind of help the heat along from hot to cold. Okay, that's the three problems that I wrote out from the custom set. The problems in the book were all fine. If you have any questions over these solutions or any of my comments on the homework, please just let me know as soon as possible so we can get everything rearranged. Okay, bye.